The air we breathe is made up of 78% nitrogen, 21% oxygen, and 1% of other gases, such as carbon dioxide. Gasoline consists of hydrocarbon molecules that contain various combinations of hydrogen and carbon atoms. When air and fuel are ignited in the combustion chamber, the mixture is transformed through a chemical reaction brought about by heat and pressure. Under ideal conditions, this process yields harmless gases such as oxygen, nitrogen, and water vapor. In reality, however, the combustion process generates several harmful pollutants, including hydrocarbons or unburned fuel, carbon monoxide, and oxides of nitrogen. Although it's normal for the exhaust gas to contain a certain level of hydrocarbons, excessive HC is a sign that one or more cylinders is misfiring. During a misfire, the hydrogen and carbon atoms fail to separate and leave the cylinder unchanged. Carbon monoxide, or CO, is another toxic substance that must be controlled. CO is produced when there is insufficient oxygen available to completely burn the fuel. Under this condition, each carbon atom is joined by only one oxygen atom. CO can only be produced through combustion and is always the product of a rich mixture. Oxides of nitrogen, or NOx, develops when oxygen and nitrogen atoms combine under the heat of combustion. Like hydrocarbons, it's normal for the exhaust gas to contain some NOx. However, when combustion temperatures exceed 2,500 degrees Fahrenheit, NOx emissions rise dramatically. Hydrocarbons and NOx emissions are commonly measured in parts per million, while CO is indicated as a percentage of the total exhaust gas sample. When the sun is shining and the atmosphere contains a high concentration of hydrocarbons and NOx, the two compounds react chemically to form photochemical smog. Although carbon dioxide and oxygen are not pollutants, most emission analyzers are designed to measure these gases. Carbon dioxide, or CO2, is a product of ideal combustion when each carbon atom is joined by a pair of oxygen atoms. Since CO2 is an indicator of combustion efficiency, it is an invaluable diagnostic gas. Identified as a percentage, CO2 will usually measure between 13 and 17% under normal conditions. Oxygen, which is also measured in percentage, is another vital diagnostic gas. A vehicle's O2 output can be used to determine catalyst efficiency, as well as the composition of the air-fuel mixture.
Here's a 50-cent word for you: stoichiometry. This is the branch of chemistry that deals with the relationships between compounds involved in a chemical reaction. While you may already know that the ideal air-fuel ratio of 14.7 to 1 is known as a stoichiometric mixture, you may not be familiar with a stoichiometric chart. This is a graphic representation of how the exhaust gases react to changes in the air-fuel ratio. Take a look.
The stoichiometric chart displays gas concentrations along the vertical axis based on the air-fuel ratio shown along the horizontal axis. Beginning with hydrocarbons, notice the relative stability of HC between the air-fuel ratios of 13 to 1 and 16 to 1. As the mixture drifts out of this range, however, it ultimately becomes so imbalanced that the engine will begin to misfire, causing a significant increase in hydrocarbons. As you can see, carbon monoxide is an excellent indicator of a rich mixture on the rich side of the stoichiometric point. At 14.7 to 1, CO is approximately 1/10 of 1%, and then drops off to near zero as the mixture becomes leaner. This is why the best indicator of a lean mixture is O2. Notice how oxygen remains close to zero until the mixture becomes leaner than 14.7 to 1. Carbon dioxide reaches its highest level at the stoichiometric point, which is why CO2 is used as an indicator of combustion efficiency. Peak CO2 measured before the converter means that all of the available fuel has combined with all of the available oxygen. Here's a look at how the gases interact at the stoichiometric point. Notice that the production of CO2 is inversely proportional to the production of the other gases. Finally, NOx production increases as the mixture becomes leaner. Notice that the highest levels of NOx are generated at approximately 17:1, which is just short of the lean misfire point.